let's consider what we could determine if we knew the initial and final velocities of an object and a time interval over which the velocities make the change from the initial to the final velocity, the net force on the object, and the mass of the object. Now, let's just start by thinking what we can get from V0, Vf, and delta t. By this point in the course, we know that from V0, Vf, and delta t, we can easily conclude the average velocity, the change in velocity, the acceleration, and the displacement. But let's construct that and then see how this net force and mass work in with that. So, you should think, what can we get, what quantities can we get by combining two of these three quantities? See if you can list all the quantities we could get and maybe write this down. And we're going to write this down as a diagram, a relationship diagram with triangles and so forth. What can we get? What can we combine, and what can we get from combining that? You should pause and do that. You should have paused and done that. If you haven't, do so now, but I'm going to go on. Okay, well, from V0 and Vf, we can get the change in velocity. We can get the average velocity. We're assuming uniform acceleration. So let's write that up here. We have uniform acceleration. So from V0 and Vf, let's see, from V0 and Vf, we could get delta V. Or from V0 and Vf, we could get V bar, the average velocity. So we should know that. If we know V0 and Vf, we know that we can get the change in velocity, or we can get the average velocity. Then, now, we can't pair up delta t with just Vf. We can't pair up delta t with just V0. We wouldn't have enough information to determine anything, but we can pair up delta t with either delta V or V bar. So, what do we get if we do that? Go ahead. See how much of the diagram you can complete. You should pause and do that. You should have paused and done that. We're going to go on. Okay. Delta V combined with delta t to give us what? Well, that gives us our acceleration. Remember that we're assuming uniform acceleration, so we don't have to specify that this is an average acceleration. Normally, if we don't know there's uniform acceleration, delta V and delta t can only give us the average acceleration over the corresponding interval. Okay, what else can we do? Well, we know V bar and delta t. We can multiply the average velocity by the time interval and get what? We can get the displacement. So, we're getting to a point where lines are going to have to cross. I could bring the delta t around this way and combine it with the V bar, but I'm just going to put a delta S down here and bring a kind of a curved line from delta t down here, so we can distinguish the curved line from the straight lines that are crossing. Okay, well, that's kind of a complete picture, because the seven quantities in terms of which we model uniformly, or in which we think of uniformly accelerated motion, are all here. Initial velocity, final velocity, time interval, average velocity, change in velocity, displacement, and acceleration. Okay, well, how do these things relate to net force and mass? What can we do? What relationships occur? Okay, well, think that through for a minute. What can we do if we know net force and mass? What are things that we can calculate by pairing up net force with some of these quantities, or mass with some of these quantities? Okay, well, you should have paused and done that. One thing we can do, net force can pair up with displacement to give us work. So we get the work done on the interval from the net force and the displacement. Now, what else? Well, we can pair up mass with acceleration to get net force. So we could say from net force and mass, acceleration we get mass, from net force and mass we get acceleration. Doesn't matter how we think of it. We're going to have this relationship. Okay, now there might be more, but let's just see what we have so far. In the first place, we got V naught, VF, delta V, and we can complete a triangle. So we got V naught, VF, delta V here. We complete a triangle, and the triangle indicates to us that we can get any two of these quantities if we know, any of these quantities if we know two. Okay, so if we know two of these quantities, we can get the third. So I'm going to go ahead and make that triangle orange so we can distinguish it from other triangles. What's the relationship that we use between V naught, VF, and delta V? How do we calculate one from the other? What's the fundamental defining relationship that defines this triangle? Well, pretty clearly that's just deciding where to write it. Delta V equals VF minus V naught. And of course then VF will be V naught plus delta V, and V naught will be VF minus delta V. Okay, that's a fairly fundamental triangle. See what other triangles there are. Well, let me just sketch in some of the other triangles. Delta V and delta T go together to give us A, so to complete this triangle, we'd bring delta V back with delta T. So we have a triangle here. I'm going to go ahead. Good heavens. Got stuff on top of my chalk. Okay, so we have a triangle here. Okay, where is another triangle? Well, there are plenty of them. Fnet and M give us A, so that we can make a triangle for Fnet, M, and A. Delta S and Fnet give us delta W, so we have a triangle here. Now, I'm going to draw the two legs of this triangle like so. I'm still debating about how I'm going to connect delta S to Fnet. I'm going to have to go through some stuff. I guess I'm going to route it here. So we have this green triangle encompassing delta S, delta W, and Fnet. What other triangles do we have? Well, we have the V bar, delta T, and delta S, don't we? Okay, so we have a V bar and delta T with delta S. So there's a triangle. Of course, these aren't literal triangles. The sides aren't straight, and so forth. You can figure out. You can try this. You can see if you can construct a picture like this where all the lines are straight. I don't think it's possible, but you can rearrange these quantities anywhere on the page and see if that's possible. The mathematical discipline of graph theory would have comments on that. Okay, and then there's at least one other triangle here. That's V naught, VF, and V bar. And I think I'm out of colors, so I'm just going to make the white line here heavier. I don't want to make it too heavy through the delta V to indicate that we have a triangle here. Okay, now hopefully you can write down these quantities and map out the relationships. But even more importantly, can we fill in the fundamental relationship for each of these triangles? So I would ask you to see if you can fill in the relationships for the yellow triangle here, for the green triangle here, for the purple triangle here, for the blue triangle here. And you should, again, pause and do that. Now, hopefully you've done so. Okay, what's the relationship among V bar, delta T, and delta S, the blue triangle? Well, that one is simply the definition of average velocity. Okay, of course I'm not going to write out the whole verbal definition, but V bar is delta S over delta T. You know, I do have an extra color. I was kind of saving this one. I said I'm going to make this one white. I'm going to go ahead and make it red. And since I'm now talking about this one, what's the relationship here? V naught, VF, and V bar. Well, V bar equals VF plus V naught over 2. Now that might be hard to read, so let's just I didn't leave myself enough room here to label this one and this one. I should have made those triangles bigger, separated those more widely. Okay, in my next version, the one that I take to the international competition, I'll try to make that a little wider. Okay, what about the purple triangle? Delta T, delta V, and A. How are they related? Well, the definition of acceleration is acceleration is rate of change of velocity with respect to clock time. That's going to be delta V over delta T. Now again, I don't have a lot of room here, but I'm going to say A, I think I can get this one in, is delta V over delta T. Okay, well, I picked up the yellow chalk. I'm just going by the color of the chalk. The yellow triangle is between Fnet, M, and A. What's our relationship there? Now I've got plenty of room. Okay, I can say Fnet equals mass times acceleration. Now, if you haven't already figured all of these out, there's still, I guess there's only about one left, isn't there? You should figure the last one out. And that's the one in green here, where we have delta S, Fnet, and W. Okay, what's the relationship there? Well, delta W equals Fnet times delta S. Now don't pay a lot of attention to the things I've added here, but I had delta W equals Fnet delta S. Should be delta W net, and this should be delta W net, because obviously this is the work done by the net force, and we want to, the work done by the net force is the net force times delta S. We'll talk about the rest of this in a subsequent video, so don't pay any attention to it now. You kind of ruin the experience.